Okay, so we've looked at trig functions in terms of the unit circle or non-unit circles, and we've done things like solved equations with them. We've used identities. We've tried to find the values of angles or ratios. Now we're going to look at sine and cosine as functions. Okay, so just like we might have, for example, y equals x squared and decide that we want to plot that like this, because if we made a table of values and we picked values for x and then substituted those in and found the corresponding values for y, those would give us our points, our ordered pairs for the points. So for example, 0 squared is 0, so we get y is 0. So this gives us the ordered pair 0, 0, and that ordered pair gives us the point 0, 0 right there. 1, 1 gives us 1, 1, which gives us 1, 1 right there, 2, 4, and so on. Okay, instead of that, we're going to look at y equals sine of x and y equals cosine of x. And we're going to plot those things, graph them, and take a look at some of the properties. So we're going to look at this, and we're going to look at this. Okay. Now, if I were to plot this, I've memorized a few key points to help me get the shape. I've memorized that sine goes through the origin. I've memorized that if I go through a quarter turn of a circle, that's pi over 2 or 90 degrees, that I get up to a maximum of 1. I've memorized that when I go to pi, I get 0 again. I've memorized that when I go to 3 pi over 2, that's 3/4 of a circle, I get -1. And I've memorized that when I get to 2 pi, I'm at 0 again. And then I can just kind of shade in my sine curve like that. Okay? Now I can derive all of these values by using the unit circle. Right? So we've done that before, but I happen to have memorized these key points so I can quickly get a picture of sine. So let's take a look here at all the special angle points to get that sine curve right there. Okay, so there's 0, 0. I've done 0, 0 in red. We know that when x is 0, or when theta is 0, sine of that is 0. Here's pi over 6. That's the special angle 30 degrees. We know that the sine of that is a half. There it is. Here's 45 degrees. We know that sine of 45 is 1 over root 2. There it is. Here's 60 degrees, pi over 3. We know that when we get sine of 60, that special angle is root 3 over 2. These all come back to those special triangles. And we know that sine of 90 degrees, or pi over 2, is 1. Okay, so here you can see the shape of the sine curve starting to develop. Now we can also calculate the sine curve in the other quadrants, or we can calculate values. So when we go into quadrant 2, notice I wrote these here in terms of pi minus the reference angle. So the first value that we hit is pi minus 60, or pi minus pi over 3, or 180 minus 60. That's 120. Okay, and so at 120 degrees, we get root 3 over 2, and we can go through all the arguments for that with a circle. Here's the point. Okay. Notice also, as we said before, that we have symmetry here, right? So if we just come back quickly to the one note, we know that sine of x is equal to sine of 180 minus x. And that this tells us that we have symmetry about 90 degrees. Meaning that when you take two angles that are the same distance away from 90 degrees, the sine of those will be the same. We can see it right here. If I go equidistant to the left and the right of 90 degrees, the heights are the same, right? And we can see it starting to show up on our other graph as well. Now I've got pi minus pi over 4, that's 1 over root 2. Pi minus pi over 6, that's 1/2. And we can see this symmetry lining up. I've got sine of pi is 0. There it is. I'll come around through the into the third quadrant now. Pi plus the reference angle pi over 6. That's going to be 7 pi over 6. When we evaluate that, we get a half, but it's negative because we're now down below the x-axis in quadrant 3. And I'm just going to fill all of these in. We could go through and calculate them all from scratch. Here we have these various values and have them evaluated for sine. And you can see you get this sine curve just like this. Okay? Now, this is one period of the sine curve, right? After this, it repeats itself again. And that's because in the unit circle, we have that angle at this point has now gone 2 pi radians, or 360 degrees, and it's about to start the journey all over again. And that point P is going to end up in all the exact same places that it was in before, and so we get the exact same shape again for the next period. Okay, so there's sine. For reference, there's cosine. Okay, cosine is the exact same shape as sine. It just starts in a different place. Okay, we start at 0, 1, and ends also at 2 pi, 1 right here. And so cosine is very similar to sine, but it's basically sine shifted. We'll talk about that more in a little bit. Okay, so let me swing back over to OneNote here. Let's look at a few key features here. Key features of y equals sine of x. What do we notice? Well, first of all, the max. The max is 1. Secondly, the min. The min is -1. Okay, so we never go higher than 1. We never go lower than -1, at least until we transform it, which is what we're going to do soon. Okay, so we've got the max, we've got the min. The amplitude. Now, the amplitude is the distance from the middle to the top. So this sine curve here, you can see it goes from -1 up to +1. The middle of it is 0. Okay, so the amplitude, I'm going to say here, is the mid to the max. The mid is 0, the max is 1, so our amplitude is 1. There's actually a formula that you can use for amplitude. You can also say that we're going to take the max, subtract off the min, and divide by 2. Okay, in this case we'd have 1 minus -1 over 2, which is 2 over 2, which is 1. Okay, so our amplitude is 1. We know that this is periodic. We can see that it's periodic. It repeats itself. Okay, and what is the period? Well, the period is 2 pi. The period is how long it takes in the x direction to repeat one wavelength. Maybe I'll even put that in here. The period is how long in the horizontal axis. So that could be theta, that could be x. Theta or x. I'll put an or, because otherwise somebody might think that that's an ordered pair. Takes to repeat the cycle or the wavelength. Okay? So because it takes 2 pi in the x direction to repeat, the period is 2 pi radians. Okay, maybe I'll put radians. In degrees, it would be 360 degrees. And the last key feature to notice is that y equals sine of x and y equals cosine of x are identical if you shift by 90 degrees, or pi over 2. Okay? If you shift by pi over 2, or 90 degrees. Okay? So let's take a look here. If I take this sine curve and look here on the left, number 21, I'm going to apply a transformation. Okay, so I have x plus pi over 2. I've got y equals sine of x, that's what's displayed right now. I have y equals sine of x plus pi over 2. Okay. The value of h is the number that's being subtracted from x. Okay, so here h is negative pi over 2. So this means we're going left by pi over 2. This here shifted to the left by pi over 2. Okay, so now if we take a look, when I shift this to the left by pi over 2, I get that. You can see every single point. If we take 0, 0, you can see that it's been shifted left by pi over 2. Pi over 2 is, well, 3.14 divided by 2, so it's about, say, 1.6-ish, 1.5-ish, and you can see that's where it is. If you take the max, the black point, and you shift it to the left, pi over 2, we get to 0. So this red curve is the black curve, sine, shifted by pi over 2. But if I show cosine on this graph and take the red one off, it's the same thing. Okay? So shifting the sine curve left by pi over 2 gives you the cosine curve. And this gives us an identity. So if we take a look here, we can actually write this as an identity. We've got now that cosine, that's what this became, of x equals sine of x plus pi over 2. Here we have an identity relating cosine and sine. This just says that cosine is the sine curve shifted left by pi over 2. Okay? Alternatively, we could take the cosine curve and shift it right by pi over 2 to get the sine curve. Okay? So we have this other identity here as well. This just says I have the cosine curve. I've shifted it right by pi over 2 because I'm subtracting off h. H is positive, so I'm going to the right, and that gives me the sine curve. Okay, and we can see that here. If I start off with cosine this time, and I shift it to the right by pi over 2, boom, there it is. That is the sine curve. Okay? Okay, so now what we're going to do is we're going to take a look at sine. Let's start with sine. And look at transformations that we can apply to this function. Okay, so we're going to review transformations, and we will apply them. So first of all, let's look at a familiar curve, y equals x squared, and apply each of the transformations to that along with sine and cosine. Okay, so I'm going to make a little table here. Suppose we have y equals f of x. That f of x could be anything. So it could be, for example, x squared. It could be, for example, sine of x. It could be, for example, cosine of x. Okay, so I have three examples here: x squared, sine of x, and cosine of x. And I have just the generic form here. Let's look at a first. Okay, so if I have a value of a times f of x, what does that do? Well, a causes a vertical stretch if a is greater than 1. It causes a vertical stretch and a reflection in the x-axis if a is less than -1. I'll say also a reflection here in the x-axis. It has a vertical compression if a is between 0 and 1. And we have a vertical compression plus a reflection in the x-axis if we have a between -1 and 0. Okay, so we've looked at this before. You looked at it last year in pre-IB. You looked at it earlier with me with various functions, and here we have it again. So now what would this look like in terms of y equals x squared? Well, we would say that y equals a times x squared. If that a is a 2, for example, we get a vertical stretch. If it's a -2, we get a reflection in the x-axis and a stretch. If it's between 0 and 1, like say, for example, a third, we get a vertical compression. And if it's negative, say -1/3, we'd also get a vertical compression, but also a flip in the x-axis. So let's have a quick look and see that in action. Here I have y equals x squared, and I'm going to move this slider, okay? So when the slider is at 1, there's our standard curve. When it's bigger than 1, we have a vertical stretch. When it's less than -1, we have a reflection over the x-axis and a stretch. And then in this range here, between -1 and 0, it's actually a vertical compression, but flipped. And in this range here, once we're above 0, it's a vertical compression, but flipped. Okay, so that's the effect of A on a parabola. What's the effect of A on the sine curve? Well, it's exactly the same. So I'll come back here to 1, if I can. It's a little bit tricky. There we are. And I'll bring up the sine curve. Okay, so pause the video for a quick second. What do you think is going to happen when I bring the slider above 1? Okay, so when A is greater than 1, well, we get a vertical stretch. There it is. These key points here, where the sine curve crosses the x-axis, they don't move because they have a height of 0, and 0 times A is still 0, no matter what A is. So these are fixed points, okay? But all the other points, the y values get multiplied by whatever A is. So there's a vertical stretch. If I come in this little region here, where I'm between 0 and 1, we get a vertical compression, okay? If I go negative and between -1 and 0, we get again a vertical compression, but a flip. Look at that difference. Okay, so normally we start off from 0 going to the right, we go up. If I put it negative with a negative a, when we go to the right, it goes down. Okay, that's because we have a reflection in the x-axis. And if a is a really large negative, well, we get that vertical stretch as well. Okay. We can see the same thing with cosine. I'll put cosine in green, right? We get the vertical stretch, we get the vertical compression, we get a vertical compression and a reflection over the x-axis, and we get a reflection over the x-axis and a vertical stretch, okay? So those are our cases. Okay, so you can see that the effect of A on sine and cosine is analogous to the effect of A on any other function that we've studied. Okay. Now, next question, what about H? What is the effect of H? Well, the effect of H is a shift left or right. Okay, so if we take a look here at the parabola, here I have it in box 5, y equals x minus h squared, and I have in box 6 that h is 0. Well, that's just the standard parabola. What happens when h increases? We're subtracting h, subtracting a positive h, we go to the right. There it goes. What if h is negative? Well, then we shift to the left, okay? That's the effect of h. What do you think the effect of h would be on sine and cosine? Well, exactly the same thing, okay? So as I go and make my h larger and larger as a positive, we shift to the right. And as I make my h larger and larger in the negative direction, we shift to the left, okay? Now notice, you could have h equals 0 here, for example, looks like that, and then you could shift, and right about here, you get the same curve again. Okay, so if you shift the right amount, your sine curve or your cosine curve will land right on where it was. So we get more identities there, right there at about 6.3, because 6.3 is approximately 2 pi. That's why you have that. Okay, but the key takeaway here is that h shifts left and right, just like always. How about k? Let's get rid of the h, and let's put up y equals x squared plus k. When k is 0, or very close to it there, there's no change. But what happens when we add a positive k? Well, we shift up. What happens when we add a negative k? Well, we shift down. What do you think the effect will be for sine and cosine? Well, exactly the same, right? So as k increases, these curves shift up. As k decreases, these curves shift down. Okay, so we have the exact same effect when we add a constant or subtract a constant after our sine or our cosine as when we add or subtract a constant after any function, including x squared. Okay. Now q. Okay, so this one is a little bit trickier. Let's bring on the regular y equals x squared. I've put my q in. Now I'm setting my q to be 1. So 1 times x is just x. This is just y equals x squared. This is our normal basic standard parabola. What will happen as q increases? Well, we get horizontal stretches and compressions, don't we? Let's take a look at how that works. So coming back to OneNote, I didn't really write down for h and k, but let's take a look at q. So q is some constant that we're multiplying x by inside the function. So here that would look like inside the function of squaring, I'm multiplying my x by q. Here that would be inside the function of sine, I'm multiplying my x by q. Inside my function of cosine, I'm multiplying x by q, okay? So these four states are analogous. And let's run through what happens. Q is different from A in that we stretch or compress by a factor of 1 over Q, okay? So if, for example, we have a Q of 2, okay? Let's suppose Q is 2. Then here, this would be y equals f of 2x, or y equals 2x squared. We would get a horizontal compression by a factor of 1/2. Okay? So you have to be a little bit careful. It's going to be a compression because we take 1 over q as the factor that we multiply all of the x's by. And because this value is between 0 and 1, it's a compression. That's the reason that it's a compression. Because the value of 1 over q is between 0 and 1. Okay, let's take a quick look at this and see it in action. If I increase this q to 2, there it is. What's happened? Well, remember q is affecting x. So in terms of x, what's happened? We have compressed, we have squished in the horizontal direction. Now you might argue that has the effect of stretching it in the vertical direction, and that is true. That's absolutely true. And I'll show you why in just a second. But in terms of the effect on the horizontal direction, it is a compression. Okay, so if we come back here, maybe I'll just put that there so you can have a look. The value of 2 for q, you always have to take the reciprocal to see what the effect is going to be. Okay, a little bit frozen here. There we go. Okay, so that also means that if q is, for example, 1/2, then we're going to have a horizontal stretch. Okay, we're going to have a horizontal stretch because 1 over q is 2. Okay, so here we have stretch because 1 over q is bigger than 1. Okay, so we've got to be careful here. And if I come over to the graph here and I make this a half, you can see we've got a horizontal stretch. It's stretching out in the horizontal direction, which is equivalent to a vertical compression, but it's a horizontal stretch. Okay. Now let me just quickly show you a connection between these. Let's take the first case here. Okay. In this first case, I took y equals bracket 2x, close my bracket, squared. Okay, so q is 2, so the effect is going to be 1/2, and because that 1/2 is between 0 and 1, we're getting a horizontal compression. The compression is because the reciprocal is a half. Okay, but I could take this and I could square it out, right? 2x squared is 2x times 2x. Let's just be a little bit slow just for the fun of it. And this is 2x times 2x. All these are multiplied, so this is 4x squared. Okay, now I've transformed the way it's looking so that I could see this as instead an a of 4. What does an A of 4 do? Well, it's a vertical stretch. Okay? So depending how you write it, you could see this as a Q of 2, which gives a horizontal compression, or an A of 4, which gives a vertical stretch. These two things are identical. Okay? They have the same effect. And in particular, when you're dealing with a parabola, a horizontal compression by a factor of 1/2 is equal to a vertical stretch by a factor of 4. The numbers that are equivalent will depend on the function. But in the case of a parabola, we can see algebraically that a vertical stretch by a factor of 4 is the same as a horizontal compression by a factor of 1/2. Okay, great. Now, let's see what the effect of Q is on sine and cosine. So here now, I'll try and put Q back to 1. Oh, perfect. I'm going to bring up sine. I'll bring up cosine as well. As Q increases, 1 over Q gets smaller. So if Q is 5, 1 over Q is a fifth. That would be a horizontal compression. So as Q gets bigger, these sine and cosine curves are going to have a shorter and shorter period. It's horizontally compressed. Okay. Now notice, in this case, this is not the same as a vertical stretch. Okay. As I say, the equivalence between horizontal compression and vertical stretch depends on the function. And in the case of trig functions, they are not equivalent. Okay, so here we have horizontal compression. Now, what would happen if Q was between 0 and 1? Let's say 0.5. Well, then the reciprocal would be 2. So we'd have a horizontal stretch. Here we go. Horizontal stretch. There it is, getting stretched out. Okay, so that's the effect of a Q between 0 and 1. A horizontal stretch. What about a Q between -1 and 0? Well, again, a horizontal stretch, because -0.1, for example, the reciprocal of that is -10. Okay, so that's a big horizontal stretch. But the negative means we're going to have a reflection in the y-axis. Now, we don't see this very often because with a parabola, for example, a reflection in the y-axis just by itself will have no effect. Okay, but watch what happens with the sine and cosine curve. Here's the reflection. Well, there, look how we have a degenerate case where Q is 0. As Q is, let's say here, well, let's just say -1. So there's no stretch or compression, but we've just changed the sign. Notice how the sine curve has reflected. Okay, if I find just a sine by itself, here, let's put up this one, you can see they're not the same. Okay, this blue one here is the original sine curve. The other blue one, the one that's showing now, is the original that's been reflected over the y-axis because of this -1 Q here. Okay. And what if I get more and more negative? Well, as Q gets greater in magnitude, let's say -5, the reciprocal of that is -1/5, which is a horizontal compression. So we're going to get a horizontal compression and will remain flipped over the y-axis. Okay? So Q has the same effect as before, but because of this function, it's a little bit different. Okay, it's different from a parabola in terms of the effects that we see. So let's summarize the effects of Q in a table here. So when Q when q is bigger than 1, then 1 over q is between 0 and 1. And so we have a horizontal compression. It's a compression because the 1 over q is less than 1 and bigger than 0. Okay. When q is between 0 and 1, then 1 over q becomes bigger than 1, and we get a horizontal stretch. When the value of q is, let's say, between -1 and 0, then that reciprocal is less than -1. This will give us two things. It will give us a horizontal stretch and a reflection in the y-axis. Lastly, when q is less than -1, then that will mean that 1 over q is between -1 and 0. This will give us a horizontal compression and, because it's negative, a reflection in the y-axis. Okay? Okay. Let's look and see what this means in terms of the period of the function. So the period, again, is how long in the x direction it takes to get one full cycle. I'll write that down. How long in the x direction or theta direction. We normally use radians, so we'll normally use x. But you sometimes you could use degrees. It also depends on the application too. Outside of math class, you would use radians and you would use degrees depending on the application. Might even use gradients. So we want to look at the period. Remember that y equals sine of x and y equals cosine of x equivalently. So this applies for both of them. Okay. Y equals sine of x or y equals cosine of x. They have a period of 2 pi. Okay, because as the point P travels around the circle, here it's gone pi over 2, here it's gone pi, here it's gone 3 pi over 2, here it's gone 2 pi, okay? So it's encountered every single possible value that it's going to possibly have, and now it starts again, okay? So when we get here, for example, at pi over 6, and we have sine of pi over 6 is 1/2, because here we have values, depends how you want to put it. Whoops. Then once we make a full circle, 2 pi, and come back to here, we're repeating again. Okay, so the period is equal to 2 pi radians. That's the period. Now, when we have a q, it's going to affect the period, right? So if we have y equals sine of qx, or equivalently y equals cosine of qx, this q will have an effect. Now, we look at 1 over q to see the effect, right? So we're going to multiply all of the x values, okay? We multiply all x values by 1 over q. That's what we do. That's why when q is a half, for example, 1 over q becomes 2, and we multiply all the x values by 2, which is why we have a horizontal stretch, because all the x values are being multiplied by 2. They're getting bigger. Now, since we're multiplying all the x values by 1 over q, the period itself is being multiplied by 1 over q. Whoops. Because that's the factor that every single x value is being multiplied by, including, if we take this here, this endpoint of 2 pi. Okay? So it's going to come out this way if 1 over q happens to be greater than 1, or it's going to come in this way if 1 over q happens to be less than 1. But either way you slice it, the period here is going to be growing or shrinking by a factor of 1 over q. So our period is 1 over q times 2 pi, or period equals 2 pi over q. Sometimes people write period as p. I'm a little bit reluctant to do that just because p has so many other meanings in math. But if we're in the context of looking at the period of a sinusoidal function, sinusoidal means sine or cosine, then it's reasonable, and you will definitely see that. Sometimes p is an abbreviation for the period. Notice that when you multiply 0 by 1 over q, it doesn't move, okay? And every curve will have a 0 point and the rest. If we look at the cosine curve, this is y equals sine x. We look at y equals cosine x. I've memorized, and you will too. We have 0, 1, pi over 2, 0, 3 pi over 2, negative 1, 2 pi, 0. Okay, and so we start to get a curve that looks like that. I was about to go further. Maybe I'll just stop it off there. It goes on and on and on. But one period comes from here to here. Again, we're going to multiply all the x's by 1 over q. If I multiply 2 pi by 1 over q, if that 1 over q is greater than 1, then it makes the period longer. If that 1 over q is less than 1, then it makes the period smaller. And 0, when multiplied by 1 over q, doesn't move. Okay, so the period itself is dictated by this formula here. This is a great one to memorize. It's not too bad to just derive it yourself if you understand what's happening here, but it's also very handy to memorize. Okay, so now that we have that, let's take a look at an example. Okay, let's suppose that we have y equals 2 sine of 4 onto x minus pi plus 1. Okay, so I've really loaded up with all the different transformations. Now, it was nice to you. I put this 4 outside the brackets here so we can identify that this is my q. Okay, I could have written 4x minus 4 pi, and you would have had to have the foresight to factor out the 4 in order to see what your q is. Okay, but I put it that way to make things a little bit easier. So here now, the question is going to ask me to just describe the effect of the various parameters and what the transformations look like, and just sort of get a sense of what this thing is here. So I'm going to go through. Well, I know that the 2 is my A. That gives me a vertical stretch. I know that the 4 is my Q. And 1 over q, which is 1/4, is what we'll be multiplying all the x's by. So in fact, here we have a horizontal compression. Okay, So we have a vertical stretch, we have a horizontal compression. Pi is h. Remember, we're always looking, what do we subtract from pi? In this, from x, in this case, we're subtracting a positive pi. So this tells me I'm going to the right by pi units. And my k is 1, positive 1. That's what's being added to the end of the function. So this tells me that I'm going up by 1 unit. Okay, so putting all of this together, what do I have? First, I'm going to sketch it myself by hand. And then after that, we'll go over to Desmos and have a look at it. Just going to put on some grid lines. Okay. Let's focus mainly on the region from 0 to 2 pi. Now, I'm going to, how should I do this here? Let's make this pi over 2, 4 squares. So this will be pi. This will be 3 pi over 2. This will be 2 pi. Whenever I'm graphing by hand a sinusoidal function, I typically break up my graph into blocks of pi over 2, at least to start. There's negative pi over 2. Okay, and let's, for the sake of things, let's say that, let's just use this as a height of 1. Okay, so we've got 1 and negative 1. Now my original sine curve has a point at 0, 0, another one at pi over 2, comma 1, another one at pi, comma 0, another one at 3 pi over 2, comma negative 1, and another one at 2 pi, comma 0. Okay, so my original sine curve will look like this and keep going in both directions. This one has been vertically stretched by a factor of 2. That means that all the y values get multiplied by 2. Here the y value is 0, so it doesn't change. Here the y value is 1, so it becomes a 2. Here it's 0, so it doesn't change. Here's a negative 1, so it becomes a negative 2. And here it's a 0, so it doesn't change. So this factor here, this parameter, affects my graph as such. Okay? And then it carries on. Q is going to give me a horizontal compression. All of my x values are going to be multiplied by a quarter. Okay? So 0 still doesn't move, but pi over 2 times a quarter becomes pi over 8. It's going to end up squished right in here. Whoops. Pi is going to become pi over 4. 3 pi over 2 is going to become 3 pi over 8. And 2 pi times a quarter is going to become pi over 2. Okay, so all of this gets horizontally compressed, and so I'm going to end up with something that looks like this. And then, of course, continues. Look at how that period has changed dramatically, right? The period used to be 2 pi. But the formula for the period, which we got before, is 2 pi over q, and my q is 4. So my period has become 2 pi over 4, which is pi over 2. And here it is. We can see it lands on pi over 2. My period has shrunk. That's the horizontal compression at factor. Now, H says that I shift to the right by pi. All of the x values go to the right by pi. So this one here ends up here. 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 Okay, so there's the shift to the right by pi. Now with this specific shift, in fact, it's not going to have an effect because you can see that if I carry on this orange one, it will look like this, and in fact, it will overlap with where it's going next. So this shift actually doesn't have an effect because it happens to coincide, make the graph coincide with itself. Nevertheless, this is how I'm shifting to the right by pi. Lastly, I need to shift up by 1. So all my points go up by 1. This one comes up by 1, 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 this one comes up by 1. I have a new midline. My midline is now going to be 1. Okay, and my graph looks like this. And it repeats every pi over 2 units. So there's another pi over 2. It will look like this. Here's another pi over 2 in this direction. It will look like, whoops. So that's very easy to do there. My midline is here. That's actually why I dot the midline in once I have it. It's very easy to go back to your original midline. You could call it a midline crisis. Okay, and then here we go. Oh, I did it again. See? Very easy to do. And so on and so forth. Okay, and this repeats. So here we have graphed this. Now, maybe we want to answer some questions about it. What's the amplitude? The amplitude is the distance from the midline to the max. That's going to be 2. We can read it right off here. Okay? So the amplitude is, the max minus the midline, which is 2. There's also a formula for it. We can take the max minus the min divided by 2. That would give us 3 minus -1 divided by 2. That's 4 divided by 2. That's 2. Okay, so that's another way to see the amplitude. Or lastly, your amplitude is always going to be A. Okay, that's the amplitude. So if you have A, you can say, oh, that's my amplitude for a sine or cosine function, for a sinusoidal, okay? And the reason why you can just pick off A is because Q has no effect on the height of the function. This is different from a quadratic, for example. Remember, with a quadratic, these things are related. For sine and cosine, they are not. Okay, so A itself is the amplitude. What if, for example, we were asked for the period? Well, the period, I'll do this in orange because this formula here was in orange. We could just use the formula, okay? So the period is 2 pi over Q. So in this case, it's 2 pi over 4, which is pi over 2, okay? So that's fine too. What if we wanted to know the midline? Okay, let's do that in pink since I was doing that in pink. Midline isn't actually an official term, but people will know what you're talking about. So if I want to find that, that is the same as the average of the max and the min, which is 3 plus -1 over 2, which is 2 over 2, which is 1. Okay, and we can see on the graph that that's correct. But it is also just K. Okay, for a sinusoidal. And for many other functions too. Well, no, that depends. But certainly for a sinusoidal, that means for a sine or a cosine. Okay, so this midline here is K. Okay, so in that sense, sinusoidal functions are kind of nice because we can use a, q, and k to read off a lot of information just directly from the function if you have the function. Or if you have a graph, you can pick out the information you need and you'll know what a, q, and k are. Okay. Typically, when I'm trying to find an equation, from a graph, let's say, or even from a word problem, I'll figure out what a, q, and k are, and then I'll find a point that has to satisfy it, satisfy the equation, plug in those values, and solve for h. And that's how I get my h. And I'm going to be doing some examples like that coming up, actually. Now let's suppose that we were asked to find the equation of this sinusoidal here. Okay, and now we could find it using sine or cosine. Let's suppose they tell us to use sine. Okay, but we could take our pick. So I've got something. Let's just call this find the equation. Okay. See Desmos graph. And I want to find it. And let's suppose I'm going to make it sine. So I have a sine of q x minus h plus k. Okay. So as I said, I can often pick off those three first quite easily. Actually, I'm going to be able to pick them all off fairly easily in this example. So I'm looking at it. First, let's get A. Okay, A is the amplitude. It's the distance from the midline to the max. Or what I tend to prefer when I'm given one like this is it is the max minus the min divided by 2. Okay, that's going to be A. That's worth memorizing, actually. Max minus min divided by 2. So when I look at it, the max looks like it is at 1.5. The min is at half. 1.5 minus half divided by 2. That works out to 0.5. So my A here is 0.5. Okay, so far so good. How about the shift? Where is that midline? Well, it is at 1. Okay, I have to look carefully, make sure I'm not making any mistakes, but it is clearly at 1. So this sinusoidal has been shifted up by 1. There we go. Okay. What else? Well, how about Q? Has there been a stretch or compression? I'm going to look at 0, 1 there. That's a key point for me because the sine curve, remember, I've memorized we have 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi 0. Okay, this is how I've memorized the sine curve as it comes from the first revolution around a circle. So this point here, right here, is key to me. Now when I look at this graph and I look to see how far is it from this first key point to this second key point, it looks to me like we're going a little bit more than 3. Okay, a little bit more than 3. What's a little bit more than 3? Probably pi. This is what I'm thinking. Now, if I am only given this graph, I cannot be any more accurate than my eyes can be. Okay, so I'm going to have to use my good judgment. If this is pi, well then halfway would have to be pi over 2, which if I pull up a calculator here, you can't see it, but I've got a calculator. Pi over 2 is 1.57 approximately. Does that look like 1.57? Well, it does. It's just over 1.5. This looks to me like it's pi. So I'm going to say that my period is pi. I'll call it P. Period is 2 pi over Q, and my period is pi. Now, if I solve this for Q, multiply both sides by Q, divide both sides by pi, I get Q is 2. Okay, so I've got a Q of 2 here. Last, I have to look at my shift. Now, if I look at this, you can see this starting point, 0, 0, it's still there. It's just been shifted up by 1, but it has not been shifted left or right. So my H is actually 0. Okay, so altogether then, I would say that my equation is y equals 0.5 sine of 2x plus 1. Okay? And if I swing back over to Desmos, you can see actually, I'll bring this back over, here it is. It is 0.5 sine of 2x plus 1. Okay, so that is the correct equation. Okay, I'm going to do one more example here. This is going to be another sketch question. Okay, sketch y equals negative cosine 4 onto x minus pi over 2 minus 0.5. Okay, how am I going to tackle this? Well, first, I've got to get a sketch of a cosine. So I am going to mostly focus on the positive portion here, but I'll focus a little on the negative as well. I'm going to put my pi over 2, my pi, my 3 pi over 2, my 2 pi, my negative pi over 2. Whoops, that's a little messy. Negative 2 pi over 2. Sorry, negative pi over 2. And I'm just going to go step by step. So, well, first, let me graph it. Now, I can see my A is just negative 1. So, I'm going to make my height about, we can come up 4 units and down 4 units. Okay, that will be 1 and that will be negative 1. Before, I had another question where I chose my height to be smaller. You remember this one? I chose my height of 1 to be smaller. I actually looked ahead and saw that I was going to be stretching it by a factor of 2 and going up by 1. That's why I made it smaller, because I knew that my final one would be already stretched. When I look at this example here, I can see from the equation that I'm not stretching it vertically, so I can use all this space. Okay, so now cosine, I've memorized these critical points. So this is the first circle, the first revolution around the circle, and then it continues. Whoops, I forgot to put in the last point here. There, that's the first one, and then it continues, okay? Continues in both directions, of course, and off it goes. Okay, that's cosine. Now, this negative 1 is going to give me a reflection in the x-axis. So 1 becomes negative 1. Zeros, they'll all stay the same. Okay? Negative 1 becomes 1. 1 becomes negative 1. Okay? And so now I'm just going to sketch it in this way. Like that. And like that. Okay? So that's taken care of the A. what's the effect of Q? And remember, we're going with the multiplicative effects first, always, and then the shifts. That's really important. So, what is the effect of Q? Well, my period is 2 pi over Q. So in this case, it's 2 pi over 4, so it's pi over 2, just like the previous example, actually. So this point here is going to get compressed all the way to here. This point here is going to get compressed all the way to here. This point here is going to get compressed all the way to here. I'm taking each horizontal value and multiplying it by 1 over Q. Okay, I'm taking 2 pi and multiplying it by 1 over Q, and I'm getting pi over 2. I'm taking 3 pi over 2, multiplying it by a quarter, and I'm getting 3 pi over 8. And now I happen to know that that's right there. You might need to do a little bit more work to find that that's the right spot. But in fact, each of these lines, I made it so that it is pi over 8. Okay, and this, where are we here now? This one comes here, and this one stays where it is. So we've done our compression. Woo, that's really steep. There we go, and it's going to carry on in both directions. Okay, now I'll do my shifting. What is being subtracted from x? Pi over 2. So that means that I'm going to go to the right pi over 2. So this point ends up here. This point ends up here. So in fact, just like the last example, this one's not going to have any meaningful impact on our final answer. And so on. And last but not least, we're shifting down by a half. So all the y values go down by a half. And again, I find putting this midline very helpful. Sometimes I'll even put in the max and the min, just so that it's crystal clear where my lines have to go. Whoops, that wasn't so great. Okay. Oops. That's part of the problem with working with one of these screens. Okay. And then that's it. Then I'd take this pink one and I would just keep going all the way in both directions, and that would be it. Okay, so to practice these various concepts, we have two exercises. Exercise 12G and exercise 12H.